So let's continue. Just recall, we went over the Dolev-Strong protocol. Like we raised a couple of questions. We were able to partially answer the first question. And I said, I saved the second question, how to reduce the round complexity with randomized protocols, to the second part. OK, and let's keep this question in mind. I'm actually not going to mention it until later on in the talk. So for this part, let's now move forward to 2018, 2019, right? So what has happened, blockchains and decentralized cryptocurrencies came around. And of course, the first system was Bitcoin. And Bitcoin was the first to really move distributed consensus to an internet scale deployment. And there, the essential idea is to have an entirely permissionless protocol where everyone can join. And to achieve this, Bitcoin relied on proof of work. Because I'm actually not going to talk about proof of work or permissionless, because Raphael is going to talk about it in the afternoon. But what people realized is that with these proof of work protocols, they're kind of expensive. They're not very nice to the environment. So there's this push towards a new paradigm. We want to implement proof of stake protocols rather than proof of work. And there's also this understanding that maybe proof of stake protocols are economically more robust than proof of work anyway. OK, so what is proof of stake? I guess maybe some of you have already heard of all these terms. In proof of stake, in proof of work, the idea is if I have computation power, then I have proportional voting power in the protocol. And in proof of stake, if I have stake in the cryptocurrency, then I have proportional voting power to the amount of stake I have. So in order to construct these proof of stake systems, we are actually returning to our roots. We are actually making use of permissioned consensus protocols, assuming existence of PKI. And we can use this as a building block to construct proof of stake cryptocurrency systems. So in fact, tomorrow, I think in Agilos' talk, he's going to talk about proof of stake. But for this talk, I'm just going to focus still on the permissioned, the classical setting. But I'm going to talk about modern protocols that were recently developed. And specifically, I'll talk about direct blockchain constructions, right? In the first part, I talked about one-shot consensus, Byzantine agreement. But now we want a blockchain. We want this linearly ordered log that keeps a publicly available ledger. There's a lot of blockchain projects and companies around, and it seems like in the past 5 or 6 years, every company has been inventing their own consensus protocol. There's a big push from the crypto community, but the crypto being the cryptocurrency community. So this actually says something, right? All these companies, they're actually they're reinventing permission consensus, which should be a problem that we understood from a long time ago. But what this is saying is that the existing protocols, before cryptocurrency, they may not be good enough for practical deployment. And that's why there's this big push. And the knowledge about this line of work is kind of scattered, because it seems like every company just has a very different protocol. So I'm going to try to at least somewhat decipher what's going on. I want to present what I think is a simplest protocol in this paradigm. It would be nice if we can actually find the protocol that we can, the same protocol that we can implement, we can teach, and basically unify this knowledge.
What's the meaning of streamline?
It'll become clear later. I'll explain all of this. OK, so let's start with the blockchain as an abstraction. Classically, actually, blockchain was studied also in the distributed systems literature. It was often called state machine replication. And essentially, we have a set of nodes. And now they not only want to reach agreement just once, they want to repeatedly reach agreement over time to establish a linearly ordered log of transactions. And this log is going to become the public ledger. OK. So this is informal. Informally speaking, I'm going to formalize these properties a little later. Informally speaking, we want consistency. And liveness consistency says that all of the honest nodes must agree on the log. People's network may have different speeds. Like your log may be a little faster than mine. That's OK, but our logs have to be prefixes of each other. Liveness says that whenever I want to buy coffee, the transaction will appear in everyone's log very quickly. OK, so still, some of these nodes can be corrupt. So like I said, blockchain also has been studied for a long time. But previously, it was not called a blockchain. It was called state machine replication. And when Bitcoin came around, there's this idea when we do consensus, we want to do batching, right? We always confirm a block at a time rather than a transaction at a time. And naturally, we have this cool name, blockchain. And all these Silicon Valley companies, actually, for the past decade, they have always deployed state machine replication protocols, often in the crash fault model, actually. And the reason why they need to do so is, like, for instance, in Google, right? They have, let's say, Google Wallet. Google Wallet is a critical service. Like, you want to make sure the service is distributed and replicated on multiple nodes, not just on a single server, right? Because otherwise you'll be putting too much faith in the single server. But once you start to distribute the nodes, there's this consistency issue that naturally comes up. Like, this is not like Facebook wall posts. Maybe if you see something inconsistent from me, that's not going to be too disastrous. But Google Wallet is something you really want strong consistency. OK. So just to formalize the definition, I'm sometimes calling it state machine replication, sometimes calling it blockchain, but they all mean the same thing. And in this part of the talk, if I ever mention consensus, I actually mean a blockchain. OK. So like I said, the goal is to agree on an ever-growing log of transactions. And I'm going to use the following notation. The notation isn't too important. It actually won't come up later on in the talk. But it's just here for specifying the properties formally. So imagine in every round T, node I outputs a log that's denoted log subscript I T. So this is node I's log in round T. And I'm going to just make a simplifying assumption. Like, every node is always going to output the longest final log. So whatever I output, it's called final. And my log should never shrink. So I don't want to deal with like log shrinking. So I'm just going to assume the protocol is nice in the sense that I'm always going to take a look at the longest final log I've seen so far and output the longest. OK. So now I need to define consistency and liveness. Again, the execution may be randomized, and I want these properties to hold for all but negligible fraction of the execution traces. And in fact, the protocols we are going to discuss use only signature and hash function. So if you assume ideal signature and hash, like there's no signature forgery, no hash collision, then you can also just assume these properties must hold with probability 1. OK. Consistency says that any honest node's log at any time must be prefixes of each other. So specifically, for any honest node I and J, for any round T and T prime, node I's log in round T must be node prefix of, this says is a prefix of, must be node J's log in round, a prefix of node J's log in round T prime, or vice versa. OK. And if the two logs are equal, we also say they're prefixes of each other. OK. So very simple definition. Any questions about this? So Liveness says, so in this protocol, these nodes are receiving transactions from some environment, right? And they want to confirm these transactions. So if an honest node receives some input, I'm using Tx to denote the input, in some round T, then shortly afterwards, like after T confirmation delay, this transaction must appear in everyone's log, every honest node's log. Okay, so specifically, we can often call this variable as the confirmation time, and we may allow the confirmation time to depend on, like lambda is the security parameter, n is number of nodes, and delta is the maximum network delay. Okay. Any questions? So we want to construct a protocol like this. The first thing to observe, like this goes back to your question earlier, why do we care about the blockchain abstraction, right? So Byzantine agreement is single shot. If we assume existence of PKI, one way to get the blockchain is just by sequentially composing Byzantine agreement.
Just these two properties?
Yeah.
Okay, can you go back for a second? So like, if my protocol does nothing?
Does nothing, it will violate liveness.
I have to receive input, okay.
This receive input is kind of like there's a, you can think of it, there's a mempool containing all the outstanding transactions. I am obtaining the mempool from the network, right, like in the Bitcoin implementation. So we call all of this, imagine there's this abstract environment that's giving me the mempool. Okay. So the first thing to observe is like, if we are happy to assume PKI, essentially everyone knows everyone's public key, then Byzantine agreement and blockchain, they're kind of equivalent from a feasibility perspective. Like for instance, if you have a blockchain, it's very easy to implement Byzantine agreement because let's say Itai is the sender. Itai can just sign a message and post it to the blockchain, and whatever message gets posted first will be the agreed upon bit. So with that, you can realize Byzantine agreement from a blockchain, and you can also do it the other way. Like if you want to construct a blockchain, the simplest, conceptually simplest approach is to just sequentially compose Byzantine agreement. Like in round I, node I is the designated sender, and then you can get a blockchain in that way. Is this confusing?
So I guess I would go back to these properties and say, if you don't have the clients, this is fine, but typically you want the clients to be able to...
Yeah, I guess in this formulation, we don't have the notion of clients. Like you can imagine if a client, in the honest...
You can't do broadcast here, right? I mean, it's kind of...
In this formulation, we don't have the notion of a client. But if you, let's say there are clients are kind of like observer nodes that don't participate in the consensus protocol. One naive way to support clients is they can just ask the nodes to, let's say these are consensus nodes, right? So they can ask the consensus nodes to vote on the log. And if you are making like something like an honest majority assumption, you can just like take the majority vote or something.
Majority assumption.
Oh yeah, for this part of the talk, I'm going to assume, in fact, I'm going to give a protocol that assumes two-thirds honest. So except, I think for...
I'm saying that if you just give me these two properties, yeah, then you have to also say that you need the majority of the nodes.
Sure, it's a little more tricky. Indeed, it's a little more tricky if it's corrupt majority, because then it's not clear what the observer, like the non-consensus node would do, right? Because you cannot take a majority vote. But if it's like honest majority, the client can, somewhat be supported easily by taking majority vote among the consensus nodes.
But this is also a very clean abstraction, right? If you think of Google or any company, they don't care about observers. They only care about the nodes running it to agree.
It's clean. I'm saying it potentially might be...
So the observer model is different and it has a different impossibility, this 1/2 addition, but even without it, this
so is... Raphael in the afternoon is going to talk about late joiners. The issue of observer is also related to people joining late. So that I can go to a very lengthy discussion about the modeling. Like for instance, we had a paper in crypto, which just took place in Santa Barbara, that showed like, the classical synchronous model is just not a good model because of this issue, because there are observers and people can join late. and people can drop offline temporarily, and you don't want to like treat honest nodes who just happen to drop offline as corrupt. But that's like a completely orthogonal discussion. So but for now, for this talk, let's just assume there are only consensus nodes. I'm not going to talk about the notion of client to make things simple. And it's kind of easy to support a client if you assume honest majority. Clients are just like non-participating observers, essentially. Okay. So now you can go back and forth between Byzantine agreement and state machine replication or blockchain, as long as you assume PKI, right? So in one direction, if we know eTai is the sender, to construct Byzantine agreement from blockchain, eTai just has to post a signed message to the blockchain, and the first message will count. Okay, and then to go the other way, want to get the blockchain from Byzantine agreement, you can sequentially compose Byzantine agreement instances, and in each instance, everyone rotates to be the sender, and then you'll be fine. I'm not going to formally prove this. It's kind of easy to believe. And what this is also saying is that in the corrupt majority setting, we can just, like, for instance, rely on do left strong to get a synchronous blockchain protocol tolerating honest corrupt majority. This is not supporting observers or client nodes because this is corrupt majority, so things are a little more tricky there. But under this notion, you can get a blockchain. Without observer, you can get a blockchain from Byzantine agreement. Okay, so this protocol is nice in the sense, like, you know, it tolerates many corrupt nodes, but it's kind of slow because every block takes a linear amount of time to confirm. This may not be what we want to implement in practice for this reason. Another question that was asked in the first part of the talk. So they're kind of equivalent, right? So why is this a meaningful abstraction? I guess there are many answers to this question. Like, one is from an efficiency perspective. Composing, like, the natural way to get blockchain is by sequentially composing Byzantine agreement, but that may not be the most efficient construction. Like, if you try to directly construct a blockchain protocol, it can often be made more efficient. And in fact, Hubert, Raphael, and I had a paper in the previous Eurocrypt, and we showed, like, for instance, for some adaptive corruption setting, we can actually, by directly constructing blockchain, we can get communication efficiency that's not known through composing Byzantine agreement. So there are results of this nature. And this efficiency is both from a theoretical and practical perspective. Okay. And I think Raphael will talk about other reasons why we need blockchain as an abstraction, because, like, once we have blockchains, we worry about how to distribute the rewards. Like, we want notions like game theoretic security, fairness. Like, we want to define notions like chain quality, which may be difficult to define if you're just considering single-shot consensus. So I'll leave this to the afternoon. But there are many, many reasons why you care about blockchain itself as an abstraction. Okay. So just maybe kind of repeating, there are two ways to get a blockchain construction. One is just through sequential composition of Byzantine agreement. And the second approach is what we will focus on in this part of the talk, is to get a direct blockchain construction. And in this direct blockchain construction, it may not be clear where the boundary between these single-shot instances are. Like, you cannot easily extract, here's a single-shot instance, and here's the second single-shot instance. Everything is streamlined, as you'll see. Slightly more cynical view, the first type is the POD-C and crypto community. This kind of results often show up in SOSP and SDI and in real-world implementations. Alessandro asked me to provide an interdisciplinary perspective. So here's how this is an abstraction that many communities care about. So Alessandro also asked me to provide a practical, like, implementer's perspective on consensus. So that's why we are going to focus on this. Okay. And, you know, if we turn back the clock to 10 years ago, before Bitcoin, before blockchains, if you wanted to implement like a state machine replication protocol, the go-to protocols would be things like PBFT or Paxos, and there are many variants of these protocols like Raft. I won't be able to provide an exhaustive list. But things have changed a lot ever since like all these blockchain companies have started working on consensus. So hopefully with this talk, you'll be able to see that we can get constructions that's kind of does what PBFT and Byzantine Paxos do, but with much simpler constructions. And I don't know if we are there yet, but it would be really nice to have a unified construction, which is both what we want to implement in practice and also what we want to teach. So I'm trying to make an effort towards that direction in this talk. Okay, so first I will review how these classical approaches work, PBFT, Paxos. I will pick the simple parts to go over. Like, I'm not going over any specific protocol. I'm going over this class of approach generically. Okay, and then I'm going to say what's what's complicated about these classical approaches, and I'm going to try to talk about how to get much simpler constructions. Okay. First, there's some tedious things to go over. We are going to assume every block has a specific format. And this is a slightly modern perspective. It's going to be a chain. And because every block has the parent block's hash. So once you look at the block, you can immediately bind it to the prefix, the prefix of the chain, just by looking at the hash. We are going to assume a block contains a sequence number. The sequence number is just like, okay, what position the block is in this long chain. And then it contains some payload, like transactions. Okay. So here is a very simple and natural protocol. Let's go back to this majority voting idea again. Like we kind of looked at it earlier, but the specific variant we looked at didn't quite work out. I'm now going to give a slightly different variant of this majority voting idea. Okay, so here the guy in the middle is called the proposer. Some of these nodes can be corrupt. The proposer itself can be corrupt too. Proposer makes a proposal. So this protocol is going to be repeated for every position, every sequence number in the blockchain, right? Proposer is going to propose a block. And now everyone's going to vote on the proposal it has received. In this case, the guy proposed an orange block. So if you are honest, you are going to cast an orange vote. If you are dishonest, you don't have to follow the protocol. You may vote for other things, like this guy voted for 2 blue blocks. And the vote is just a signature on the proposal. Okay, on the proposed block. Okay. So now we just basically collect all the votes. And once we collect 2/3 votes on the same block, we are happy, like there's enough confidence, and we believe that this block is confirmed. So in this variant of the voting protocol, we want to count exactly 2/3 votes. And I'm going to say this very soon. We are going to assume at most less than 1/3 of the nodes are corrupt.
And you know N.
Yeah, we know N. It's a PKI. Everyone knows everyone's public key. We know who is participating in the protocol. Exactly who is participating.
PKI doesn't mean that you know that everyone is participating.
Okay, I'm going to assume a strong PKI model where everyone knows who's participating and everyone knows who everyone else is public key. Okay. And so in the rest of the talk, I'm going to call a collection of 2/3 votes a notarization. Just convenient terminology. These votes have to come from distinct nodes. Okay. And the most important thing about this simple protocol is that the honest nodes must vote uniquely at every position. like let's say we're trying to agree on the 5th block. I'm going to receive a proposal from the guy in the center. I'm only going to vote on one thing. Like if he gives me 2 equivocating proposals, I'm just going to vote on the first thing I hear. So this is important for proving consistency. And let me just give a very simple consistency proof that shows essentially whatever is confirmed must be unique at every position. Okay. More concretely, let's just focus on a specific position, right? So imagine Itai has heard 2/3 people voting on the blue block, and maybe Raphael has heard 2/3 people voting on the orange block. I want to show that these must be the same block, right? Because Itai is going to confirm this one, and Raphael is going to confirm this one. So let's look at the 2/3 voters that have voted on the blue block and the 2/3 voters that have voted on the orange. The intersection must be large, as long as there are fewer than 1/3 nodes corrupt, right? Because 2/3 is like 4/3 minus n. So the intersection must contain at least 1/3 number of nodes. The intersection must be large regardless of how many people are corrupt. But because few people are corrupt, there must be an honest guy in the intersection. The intersection must be at least 1/3, less than 1/3 corrupt. So there must be an honest guy in the intersection. And remember that this honest guy is going to vote uniquely. And the only reason that this could have happened is these 2 are the same block. Okay, so this says if you assume 1/3, less than 1/3 corrupt, and as long as you count sufficiently many votes, and here sufficiently many means 2/3, then you enforce uniqueness agreement at every position. So everything seems great. We have consistency as long as 2/3 of the nodes are honest. And the consistency proof doesn't depend on the proposer being honest, right? Like the only thing I'm using is that honest people vote uniquely, but the drawback of this protocol is that liveness depends on this guy in the center. He has to continuously continue to behave honestly for the protocol to make progress. Like if the guy in the center, he drops offline, he stops making proposals, no progress will be made. If he starts making different proposals to different people, then everyone will vote on different things, and nothing will collect enough votes. So the protocol will come to a halt in that case too. Okay. So essentially, now the goal is to strengthen the protocol such that liveness doesn't need the stronger condition. Like we want to be able to obtain liveness only assuming 2/3 honest, without having to rely on the guy in the center. And how do we do that? So this is where most of these classical protocols get somewhat complicated. Just at a very high level, the way these classical protocols like PBFT, Paxos, and other variants, the way they work is that there are 2 different modes of operation. There's the normal path, which is kind of just like what I talked about. But typically, the voting has to continue for a couple more rounds to kind of get ready for the recovery path. But it doesn't matter. Like basically, they are just voting in the normal path. And let's say when the proposer becomes corrupt or he crashes, and then the system goes to a recovery path where people try to reach consensus and switch to the next proposer. So when they want to switch to the next proposer, they have to kind of finalize the log that they have already agreed on, like because we may be operating at different paces, like your log can be a little bit longer than mine. So we reach agreement on that, and then I'll switch to the next proposer. So this part actually requires full consensus. I mean, in some sense, because here, like we only have consistency, right? We don't actually have liveness, because liveness depends on the guy in the center being honest. But here we want to essentially solve consensus problem in 4, and that's why this part gets like kind of involved. And
how do you define simple and complicated?
I don't have a good mathematical definition, but I guess most would agree that this normal path protocol is fairly simple. Right? It's just like it's very natural. You vote, you propose, you vote, you reach agreement. Okay. So when you implement these systems, the undesirable thing is that most of the time, your system should be operating in this mode. But if you look at the code base, like most of the complication is here. That's where all the bugs are. And that's where all the annoyance comes from. So now, like, from a practical perspective, it would be really nice if we can get just full-fledged consensus, but perhaps just as simple as the normal path that I've shown, like some very natural voting protocol, but we get both consistency and liveness, assuming 2/3 honest. So how do we do that? I'm just going to take this normal path protocol that I've mentioned. I'm going to make a couple tweaks to the normal path protocol, and I'm going to show that it gives you full consensus. And a couple tweaks, I find them quite natural, but I'm going to try to explain it to see if you guys can find it natural too. Okay. So what I want to say is, like, the ideas I'm talking about is kind of, there's a line of work that, some of which came out of the crypto community that's been developing these ideas gradually. All these protocols look very different, but I'm just trying to, I'm trying to
unify.
Yeah, maybe simplify things to the best I can. So the first relevant paper, actually this Casper is this Vitalik and Virgil's this finality gadget. Like, they want to use this on top of the Ethereum proof of work chain to periodically reach finality, stronger finality. And then there's subsequent works that also kind of follow this paradigm. Like, Hot Stuff is the first work that proved both consistency and liveness. And the protocol I'm going to talk about today is closest to Pala, which is kind of an improvement of Hot Stuff. Okay.
Tendermint should also be mentioned here, right?
Yeah, I guess I'm just confused about Tendermint because they had an earlier version that was actually sequential composition of one shot, but maybe later they changed. So I no longer know their latest version, or whether it's a direct blockchain construction or not. Okay. So just to quickly revisit, like I said, this is the blockchain format, the block format we are going to assume. It's kind of modern because it's a chain, right? Every node refers to the parent's hash. I'm going to change the sequence number to epoch number. And we'll see what this means. And then there's the payload, which is the transactions. So imagine all these nodes, they have clocks and that tick, let's say, every second. You can get rid of this assumption, but for now, let's just simplify things and assume people have clocks. And every epoch, let's just assume it's 1 second. And we can assume the network is synchronous, so we can make a round trip within a second. Like when Itai and I exchange messages, a round trip can always end in 1 second. Any questions? Okay, so this is just like some tedious setup that I want to go over.
This is very different than like PBFT and Paxos, right?
I mean, PBFT, Paxos, this chaining idea is not essential to PBFT and Paxos.
Assumption that every message takes 1 second.
I will get rid of the assumption later. So let's start by assuming synchronous. But in the end, after I show you the proof, I'm actually going to tell you, look, the proof doesn't rely on synchrony. The consistency proof doesn't rely on synchrony.
So let's not assume it.
Yeah, for now, just for simplicity. Like, I don't want to introduce partial synchronous yet. I'm going to explain exactly what is partially synchronous after I show the consistency proof. Okay. so like, earlier we had the problem, like when the proposer is corrupt, we want to switch proposer. So now we just want to do it more aggressively. We want to say, the protocol is going to continue in epochs, and every epoch allows you to switch proposer. So if we can do that, then we don't need a separate path for proposer switch, right? So for simplicity, we can assume in in epoch I. Epoch is different from round, right? Epoch can contain multiple rounds. It's one round trip can be implemented in one epoch. So in epoch I, node I is going to be the proposer. So this is publicly known. We can support other proposer rotation policies, but for now, let's stick to the simple one. Okay. We need to know what's the notion of freshness for a block or a chain. And this definition is very natural. Like if the block, remember the block encodes the epoch number. If the epoch number is larger, then the block is fresher. And you can define the notion similarly for a chain, right? Because this is like a hash chain, a block actually just uniquely binds to the entire prefix. So in some sense, blocks and chains are kind of aliases of each other. So if you can define freshness for a chain just by looking at the last block of the chain. Okay. So I'm going to describe a protocol that's just almost the same as before. Like in every epoch, a proposer will propose and everyone will vote. And then when you collect enough votes, you confirm. With a couple tweaks where you check like an additional condition when you vote. Okay. So in this protocol I'm going to show, like if everyone were honest, then things would be nice and you would see exactly just a chain like this where the epoch numbers will increment for every block. But like in real life, as we said, some nodes can be corrupt. Right? Remember now, every epoch people are rotating to be proposer. Like for instance, if the second guy is just crashed, then he may not make any proposal. So we actually have to allow the chain to skip epochs. So we no longer require that the epoch numbers are continuous in the chain. We would be happy as long as the epoch numbers like strictly increase. But you can skip epochs. Like sometimes you may see forks. Let's say in this case, both chains are notarized. So I'm going to introduce like how to deal with such forks. At this moment, it's not important yet. Okay. Any questions about the setup? So here's just like some other tedious assumptions I have to mention. We are going to assume like the honest nodes are receiving messages from the network. And for every message that's fresh, I'm just going to echo it to everyone. Like, so if I see something now, you'll see it in the next round. Okay. If I see it now, you'll see it soon, like within one delta, with one delta where delta is maximum network delay. Okay, and so like the messages we receive, right? They're blocks, they're proposals, blocks, or votes. So I can locally maintain like every block that has been notarized. And since these blocks have parent pointers, like I can reconstruct the chain on my local node. And imagine I will keep track of the freshest notarized chain I've observed in every round. Like if I ask a node, what is the freshest notarized chain you have seen in round 5, he's able to answer that question.
Can you define a notarized chain?
Oh, so yeah, sorry. Notarized, again, is like every block in the chain has to have 2/3 votes from distinct people. So in the protocol I'm going to describe, every epoch, the proposer will make a proposal, people will vote, and if the block collects 2/3 votes, it becomes notarized. But notarized doesn't mean final in this protocol. So you want to be a little bit more patient, like not just confirm. Like in the earlier protocol I talked about, I immediately confirm the block once it's notarized. But here you want to just be a little more patient. Okay, but the definition of notarized is still the same as before, just 2/3 votes from distinct people. Okay. Any questions? Okay, so here's essentially the protocol. The blue part is kind of the change. Oh, there are two tweaks. This is the first tweak, and then there is the second tweak. Okay, so the protocol progresses in epochs. Every epoch is a second. At the beginning of the second, if I'm the designated proposer of the epoch, I will propose the next block. So I need to decide which chain to extend it from. And very naturally, I want to pick the freshest notarized chain I've seen and extend the new block from the freshest notarized chain. So I'm just going to send this proposal to everyone because the block contains the hash of the parent block. Like everyone knows where the block is extending from. So now people, when they receive the proposal, they're going to vote. There are a couple sanity checks. Like for instance, when I receive the block, I want to make sure the block extends from a valid chain, right? It cannot be like a dangling block where the parent pointer points to nothing. And not only so, I want to make sure the parent block is notarized. Like I've already received enough votes for the parent block. Okay, so making sure the block proposed is extending from a notarized block. The no double vote for each epoch is the same as before, as this simple protocol I talked about earlier. I don't want to vote twice in the same epoch. And the last condition, which is a little bit subtle, this is the new condition. I want to make an additional check now when I vote. But this check is also intuitively, it's also very natural. Because so essentially what I'm checking is that the parent block must be fresh enough. Like because if the proposer is corrupt, he can try to throw away all of the work that people have done in the middle and try to, like now it's already epoch 100, but he tries to extend from epoch 1. And that's obviously not okay, right? Because then all the work in the middle is like thrown away. So I just want to make sure this parent block is reasonably fresh, like it's some block that was notarized recently in the past and not too long ago. So precisely what is fresh enough, like you can define it precisely. I'm going to check that the parent block is at least as fresh as the freshest notarized chain I've seen, not right now, but just a little while ago, at the beginning of the previous epoch. Like to check fresh, I'm basically comparing with my own view. But I don't want to compare with my own view right now, because maybe the proposer's network is just a little bit slower than mine. And I don't want to kill Liveness just because this proposer is honest. His network is a little bit behind mine, so his view is a little behind mine. So I'm going to compare the proposer's proposed block with what I have observed just a little while ago. Let's say at the beginning of the previous epoch, the freshest notarized chain I've seen is at epoch 10. Then I will insist that the proposer must extend from a block of epoch 10 or larger. Cannot be smaller. Smaller means too old. And maybe the guy is trying to throw away a lot of work that has been done in the past. Okay, I'm only going to vote if this condition is satisfied. This additional condition is satisfied. Is this confusing?
You won't be able to remove the assumption of the second if you're not taking the most stretches.
But once we go over the consistency proof, you can draw that conclusion. Whether consistency requires synchrony. So that I think we can just go over the consistency proof and you'll see. Liveness does require a period of synchrony. Any questions?
So again, you're happy with something that's, you've seen something notarized in 10 and you're happy with something that's notarized in 9? You'd vote on it?
So let's say now it's epoch.
You've seen a notarized thing at 10. Somebody gives you something notarized at 9. You're happy to vote on it?
Maybe we can be a little more precise. Let's say now is epoch 10, and I receive a proposal from you. You're the proposer. The proposal is extending from a notarized block of epoch 8. So I'm going to ask, is this parent block fresh enough? And how do I determine that? I'm going to check, okay, just a little while back, at the beginning of epoch 9, now it's epoch 10, right? At the beginning of epoch 9, what was the freshest notarized chain I've seen? Maybe it was epoch 7, then it's okay, because 8 is bigger than 7. But maybe a little while ago, I've already observed, let's say, epoch 9. Oh, this is not possible. I guess I gave a bad example. Like I guess, let's say now it's epoch 10. And then you propose some block to me, and let's say it extends from a notarized block of epoch 5. And then, so you propose some block of epoch 10, right? This is the current proposal. I receive this. I now ask, what was the freshest notarized chain I had seen at the beginning of epoch 9? Okay, what is the freshest notarized chain I've seen at the beginning of epoch 9, which is currently it's epoch 10. Okay, so maybe if the answer is 6, then I will reject the proposal and not vote. If the answer is 5 or smaller, I will say, okay, this proposal is okay, I'm going to vote on it. It's fresh enough.
If it's 5 and it's the same one I have.
But that's the parent block. So with the new one.
Yeah, this has to be as fresh, but actually you have uniqueness at every position once it's notarized. So if it's epoch 5, it must be the same block. Okay.
Is this double safety check for boxes?
So this is the first tweak, and the second tweak is just basically when I consider a block as final. Like in this protocol, like you want to be a little bit more patient. Notarized is not final yet. Because if, let's say, block 3 is notarized, the only thing this says is that I know block 3 is notarized. It could be like later on, like when this guy makes a proposal, it skips a bunch of things and extends from block 2. Right? So if this happens, this notarized block is not going to survive in the chain at the end of time. So we want to be a little bit more patient. And here's the finalization rule. It's very similar to Bitcoin. Right? In Bitcoin, I get my longest chain. I chop off the trailing 6 blocks, or chop off the trailing kappa blocks. And I don't consider the trailing kappa blocks final. But here, I'm going to just look at all the notarized chains I have. And if I ever observe 3 consecutive blocks notarized, 3 consecutive, then the first of the 3 up till here is notarized. So if I ever observe this, okay, here are 3 that's consecutive, they're all notarized, so this prefix must be final. And here again, I have 3 consecutive blocks, they're all notarized, and I chop off here, and this whole prefix is final. Okay, so that's the whole protocol. So two tweaks to the normal path.
Why 3?
I will show a proof. So first, I will explain the proof intuitively without any parameter, and then I'm going to plug in the parameter. So this 3 is actually, this protocol is, these parameters are tunable. Like if you throw in some other tweaks to the protocol, you can make the 3 2. But I'm just going to try to do what I think is the simplest instantiation.
So you are taking one protocol which is long and you are pipelining it to...
Exactly, that's why it's called streamlined blockchain, right? You can think of it, there's some single-shot consensus, and typically these constant round single-shot consensus protocols work by voting, but you have to vote for multiple times. So let's say you take a single-shot consensus. The first round of voting is called prepare. The second round of voting is called commit. Like now, I'm going to use the next block's notarization to serve as the previous block's commit voting round. So that's how these things are obtained. Okay. So why does this work? I mean, the idea here is that I just want to be a little bit more patient, because like I said, if this block is notarized, it doesn't mean it'll get picked up later. Like it could be dropped. Like maybe this guy didn't see this notarization early enough before he made the proposal. So then it gets lost at the end of time. So I only want to finalize things that I'm sure will not get lost at the end of time. And how can I be sure of that? I want to make sure many people have seen the block notarized early enough, right? So in this case, many people have voted for, because 4 got notarized, it must be that many people have seen 3 notarizing in epoch 4. Because I'm not going to vote on, remember the protocol, I'm not going to vote on this block unless it extends from a notarized parent. Okay, so if many honest people have seen 3 notarized and early enough, let's say in their epoch 4, then later on, if this guy tries to cheat and not pick up block 3, then they are just going to refuse to vote. Like all these people will say, okay, you're not proposing from a fresh enough parent. Like you're trying to drop all this work in the middle. I'm not going to vote for your proposal, right? So waiting a little bit longer, waiting for the next couple blocks to also get notarized, makes sure essentially many people have seen this block notarized, and not only so, they have seen it notarized early enough. Okay. So again, in this picture, like all the dark blue blocks are notarized, and the light color ones, all the dark blue ones are final. Everything's notarized, but the dark blue ones are final, and the light color ones are not final. Okay, so how do I turn this intuition into a formal proof? So first, just recall, I guess maybe I'll run over for 5 to 10 minutes. But you guys can, if you want to go to lunch, you can leave a little early. Okay, so first, every epoch can only have one unique notarized block. And this was proven in the first part of the talk using this pigeonhole principle. Okay, just keep that in mind. So in this specific example, there are some uninstantiated parameters. I'll instantiate it later. But for now, as I said, many people, this block gets notarized. It must be that many people have voted for it, right? And then the honest nodes are only going to vote for this block in their epoch 4, and they're only going to vote for it if they have seen 3 notarizing epoch 4. So this means many honest people have seen 3 notarizing epoch 4. And all of these honest people, later on, if they receive a proposal from the 6th proposer, and this guy tries to drop this block, like he doesn't pick up this block, then all these guys are going to refuse to vote here, and then such a bad proposal will not get notarized. So that's how the proof is going to work. It's kind of easy to just plug in the parameters. If 4 is notarized, there is a set S containing at least 2/3 n minus f honest nodes, right? Because notarized means 2/3 votes. Among them, at most f come from corrupt nodes. The rest must all come from honest nodes. So all these honest nodes have voted for block 3 in their epoch 4. It means they have seen block 3 notarizing epoch 4. So later on, all these nodes, S, if some guy makes a bad proposal that tries to drop this block, all these guys in S will refuse to vote. And if you do the math, if all these guys refuse to vote, how many nodes can actually end up voting for this bad proposal? It would be n over 3 plus f. And f is less than 1/3. So that's not enough to make a notarization. So such a bad proposal is never going to get notarized. Okay, so this is still proof for this picture. I guess I won't go over this, but you can just plug in general parameters. Like this can be any e, epoch e, e plus 1, e plus 2, and e prime plus 1, e prime plus 2. It's same proof, but okay. Live disproof, go over it very quickly. whenever there are 3 consecutive epochs with honest proposals, you make progress. And the only thing you have to show here is that the only danger here is that people won't vote on the honest guy's proposal. And we just have to show that that's not going to happen. And this relies on the fact, so the only reason why people will reject this proposal is because the parent is not fresh enough. And everyone's comparing the proposal's parent with what they have seen just a little while back, right? So all you have to show is if I've observed this, let's say block 5 notarized a little while back, at the time you make a proposal, you also must have seen block 5 notarized too. So you cannot make an unfresh proposal if you are honest. So that's just, I won't go into details of the proof, but that's just like, this is a pretty simple proof. Okay, so now, I'll try to wrap up fairly quickly, but here is a good time to revisit the wrong complexity question. Earlier, I've assumed that the proposer rotation policy is like 1, 2, 3, 4, 5, 6. So if the adversary is honest, he can corrupt 1/3 n continuous proposals, and you would have to wait for linear amount of time for confirmation. But had you selected the proposer at random, imagine you pick a hash function. Like in the beginning, adversary decides who to corrupt, and I pick a random hash function. And every epoch, I'm just going to use this random hash function to select who's the designated proposer. And in this case, you only have to wait for expected constant number of epochs for this condition to occur. And therefore, you can reach confirmation in expected constant number of rounds, assuming that corruption is static. In other words, this hash function has to be chosen after the adversary decides who to corrupt. If it's adaptive corruption, you can achieve the same, but by adding a little more complication to the protocol, I'm not going to show how to achieve the same with the adaptive corruption. Okay. So maybe I can just try to conclude at this note on partial synchrony, and I'll skip the rest. One thing to observe, like you may want to think about this a little longer to realize this, but eventually if you stare at the consistency proof for long enough, you'll realize the consistency proof doesn't rely on any synchrony assumption at all. Like the only thing you are assuming is that people's epochs are increasing. Like my epoch can never decrease.
You're claiming that without synchrony reaching, you can reach consensus no matter what?
Yeah, in the partially synchronous model, you can reach consensus. So this is...
Eventually, you will be synchronous.
Yes, exactly. The interesting thing is the consistency proof doesn't rely on synchrony, but the liveness proof relies on synchrony because the only way I can make progress is if the honest proposer is going to propose something, extend from some parent that's not too old. And to make sure that guarantee is respected, whatever I know now, you must be able to know a little bit, just a little bit later.
It's not enough. You want the honest proposal and synchrony.
Yeah. So liveness proof relies on synchrony. Whenever there are 3 consecutive honest proposers, progress will be made as long as when you propose a block, the parent is not too old. And this can be ensured if, let's say, whatever I see now, you're going to see a little bit later. So that's the only place where the synchrony assumption is used. Okay, so this actually brings us to, I've actually, weakened my claim. We can actually this is a protocol that works in the partially synchronous model. And partial synchrony was a really beautiful model defined by Dwork, Lynch, and Stockmeyer. There are 2 versions of it. I'm going to focus on the GST version. So in this version of partial synchrony, the protocol receives an estimate of the narrow delay. Let's say I estimate messages will get delayed in half a second. And I'm going to let the protocol know that. When I run the protocol, it could be that the actual network delay is much, much longer. Like, sometimes I get partitioned, the message takes an hour to deliver. It's much longer than what I had estimated up front. But it doesn't matter. Like when the network gets partitioned and everything, we want to make sure the protocol will still respect consistency. But it could be that liveness will stall when this delta assumption is violated. Because for instance, if the network gets partitioned, of course, like, you get stuck there, you cannot make progress, or you're always waiting to collect enough votes. But people's votes cannot reach you because they're isolated in the network. Okay. And then the protocol will make progress as soon as you reach a period of synchrony. Let's say as long as at some point this delta assumption is respected, then during that period you're going to start making progress. But up front, the protocol doesn't know when the period of synchrony is going to happen. Like it could happen now, it could happen later this afternoon. I have no idea. So that's the model. In this model, it turns out that 1/3 is the best you can defend against. So the protocol I talked about is also actually tight in terms of resilience for partial synchrony. This well-known theorem, the proof is very short. Maybe Raphael can talk about it in the afternoon. So just to summarize, streamlined blockchains, I want to kind of get a full-fledged consensus just by the proposed vote paradigm. It's always proposed vote, proposed vote, proposed vote, confirm, confirm, confirm. And the reason why we don't need a separate path for view change, or for view change is also another name for recovery path. The reason why we don't need that is because now every epoch essentially allows you to switch proposer. And from a technical perspective, actually what enables this streamlined approach is this is taking everything apart. Like you need a very simple, full-fledged consensus protocol to implement the view change. And once it becomes really, really simple, you can kind of sneak it in there and make everything streamlined. And in comparison with like protocols of the past, like PBFT Paxos, like I think Itai would have said these previous protocols imply they, in some sense, if you take it apart, the view change has n² bandwidth. But here we are actually implicitly using a view change protocol that's linear in bandwidth. But what I want to say is, like in practice, the bandwidth of the view change, I don't think it's like the most important thing, because view change actually shouldn't happen very often, right? It only happens when the current proposer is faulty. It only happens in rare occasions. But what is really important, I think, is the simplicity of the protocol, like for practical implementation. And I think, yeah, we should have, ideally we should have a unified protocol. That's what you want to implement, also what you want to teach. And I don't know if this is there yet, but we can move towards that direction. And I'm just going to skip the rest of the talk. You can get better resilience in the synchronous model following exactly the same paradigm. Like this is the whole protocol. We have, with some other tweaks, you can achieve additional robustness and performance properties. I don't want to go into the details there. Thanks.
Are you claiming, is this adaptive security?
As the way it's presented, it's like it's adaptive with longer confirmation time. Like if the adversary corrupts continuous proposals, like eventually it's going to run out of corruption budget. At that time you'll make progress. If you want to get expected function run with adaptive corruption, like one known technique, I think this is from the Katz paper, is you would have a round where everyone pretends they're the proposer, they all make a proposal, and then you do the random leader election to decide who's actually the proposer. So if you have that tweak to the protocol, you can get adaptive. You may need to have a leader election protocol that's adaptive. Assuming that exists.
Or just the VRF, right?
Yeah. I mean, VRF is like
different things. But maybe
Yeah, you could use the VR.
Yeah, that's what we did, no?
VR, I guess, makes different set of assumptions.
Yeah, like the VRF requires some, there's some secret visibility. It's kind of like formally proven is VRF thing requires a CRS, actually, unless it runs.
Yeah, it's kind of, you need an adaptively secure VR.
Yeah. It's like we have some ugly constructions.
It's a little more
with
complicated because like here you need 3 consecutive epochs, but I guess you can get that with
Yeah, with some reasonable probability for it.
So you have to parameterize it.
Yeah.
Great. So we resume at 2 with Havel discussing what the consensus.
Elaine, can you put the previous slide?
Huh?
The previous